axial, well, then some nice materials she will name to us. Thin film heterostructures. Yeah, please.
Thank you. Okay, my name is Flavia. I'm a postdoc at Brazilian Synchrotron Laboratory. The results that I will show here is an ongoing, it's from my postdoc, it is an ongoing working. And, okay, the name of the presentation is the strain analysis of 3D dislocation in epitaxial barium titanate Barium-Strontium manganite thin film actor structures. And I'd like to start explaining why strain. We know that we know multiferroic materials. We know the multiferroic properties may be coupled with some coupling properties. And we know that in the case of magnetoelectric composite, we have a phase with ferroelectric phase and a ferromagnetic phase, and they are connected. And this connection, the strain from this connection, makes the strain between these coupling properties at the ferroelectric and the the strain between the piezoelectric properties and the piezoelectric phase and the magnetic restrictive phase plays the role of the magnetoelectric coupling, this kind of composite. So we would like to investigate this strain field and the effects on the crystal lattices of ferroelectric and ferromagnetic perovskite bilayers. And to do that, we will use transmission electron microscopy. Actually, most of the images are scanning transmission electron microscopy. And we are using geometric phase analysis to understand these strains and these defects. A brief outline of my presentation. I will briefly introduce the geometric phase analysis method and show several examples of displacement and strain maps in ferroelectric materials and also in defects. I'll explain a little bit about misfit accommodation, and then I will go to the sample preparation, sample growth, and sample preparation to transmission electron microscopy. And then I will show our results until now and conclusions. Geometric phase analysis is a measurement of the displacement of the atomic columns in a transmission electron microscopy imaging. And this displacement is from compared with perfect lattices, and our perfect lattices is our substrate. And this strain comes from the gradient of this displacement field. This method is used to study the mismatch between films, the twins between layers or in a crystal, and dislocations effects. Here I have an example of the displacement map in a ferroelectric thin film. These are lead titanate. And from the displacement map, we can see how the polarization goes through the 90 degrees domain wall. That is a twin domain wall. I have also an example of a strain map in the ferroelectric PZT that we can see the strain field, how it is in two directions as it is a matrix. We have here then the strain field at two different, at the plane and outside at the growth direction and in the plane. I show also an example of lead titanate growth in a lanthanum-illuminated substrate. That show here we have this difference of colors shows the mismatch of the film. And in several places indicated here, we have the defects. We have dislocation at the interface that are the misfit dislocation. When you grow thin films and on epitaxial thin films, on the strain in the epitaxial thin films, you may have three kind of misfit accommodation. The veneer of a misfit, you may have homogeneous strain, or you may have misfit dislocation to relax the lattice on the growth. Going to our work, we grow then lanthanum-strontium manganite on strontium titanate single crystal. This is our ferromagnetic layer that is ferromagnetic at room temperature. That's why we choose. Oops, we choose it, and it has a strain misfit, a small strain misfit compared to the strontium titanate, and then we grow our ferroelectric layer, barium titanate, on this lanthanum-strontium manganite that has almost a 3% of strain, misfit strain. This sample were grown at the PGMB line, the one that I do my postdoc, and we grow by pulsed laser deposition. We choose appropriate conditions of post-annealing or even deposition conditions, and that we can talk if someone wants. And our to perform the transmission electron microscopy measurement, we used the most conventional method of preparation with mechanical dimple and ion milling. This part of the work were performed at the Brazilian Nanotechnology Lab that is at the same campus of Brazilian Synchrotron Lab. And before I start, let me drink a little bit. That is also an open facility in Brazil where we can do this kind of work. So going to the preliminary result, here I have the surface topology of our substrate before the growth. We have a roughness of about 1 lattice parameters of the strontium titanate. And after we grow the sample, we have this kind of grains or island. Actually, island. From the transmission electron microscopy, we can see, actually from the electron diffraction, we can see that our growth are epitaxial. And when we look more at the transmission electron microscopy result, we can see that after we start to grow our barium titanate, we have this kind of island in our sample. Look close to the interface. Okay, here we have a pretty perfect growth. And here we have barium titanate, we have several islands. When we look close at the interface, we can see that something happened few nanometers after we start the growth of barium titanate. To understand this better, thinking about this kind of island, we know this as the layered and island growth. So we start the growth layer by layer, and something happened with the lattice, and then we have we start to growth island. So to understand better, we perform then the scanning transmission electron microscopy in aberration corrector microscopy, where here now we have the Z contrast. And to see better the interface, I have this image. And to show you better what happened a few nanometers after we start to grow the barium titanate, I performed then a Fourier filter of 1001 direction. That okay, I did the Fourier transform image, and then I masked one direction and did the inverse of Fourier transform to see what happened at the growth direction. And here we have that several nanometers after the interface, we have the dislocation. And this dislocation happens every 10, 30 nanometers. 20 or 30 nanometers. And now, to see better, we'll perform the strain map. At the plane direction, what we have here is that, okay, we don't have much strain interface here, but exactly when the barium titanate start to grow, we have about 7% of strain. And then we have the 3%, about 3%, exactly like we would like to expect. And when we go to the other direction, we see here the dislocations. We see actually an uniform homogeneous strain with the dislocation at the other direction. Going more inside the barium titanate film, what you see is the same. Close the interface, we have this relaxation after the dislocation. But when we see the dislocation, we can see them combined in two dislocation in all of the film. And this is not at the interface. We don't know if it is only due to the misfit accommodation. When we look at the other work with this, we found two lead type PZT, where they see several several things on the image, and when they did the Fourier transform in a specific direction, they see this dislocation. But in this case, this dislocation that is not a misfit dislocation, but in this case, they are pointing, they are in pairs, also as mine, and they are pointing to each other here. And these are the 3D dislocation. This 3D dislocation may happen if we have a misfit dislocation. If you may appear when you have an accommodation between islands, or the formation of loops, or when you are growing the sample, actually when you are cooling the sample, this 3D dislocation may form. We didn't find this dislocation at the opposite direction. We may look at in this case, they were looking at the 110 direction. The sample were cut at 110 direction. And so to look for this at another direction, we will need to cut the sample again. But we have different dislocation, not exactly misfit dislocation, not exactly misfit accommodation, but we also have pairs of dislocation. So, to conclude, we observed the layered and island epitaxial growth, and we observed the sequence of dislocation in our ferroelectric layer. This layered and island epitaxial growth may exist through our defect, or maybe our defect exists because our barium titanate growth as a layered island. And maybe to application is the most important question. What is the influence of these dislocations? What is the pair of this, if it is a 3D dislocation, what is the pair of this dislocation? And the opposite. And of course, what is the influence of this on the properties of the films? And that's all. Thank you.
All right, well, thanks for being perfectly on time.